Assalamu alaikum wa rahmatullahi wa barakatuh. So today our lecture number 12. In lecture number 12 we will start with the topic independent trials. So before that we have seen sampling without replacement and sampling with replacement. So we have seen different ways how we can calculate the number of outcomes in a sample space. So independent trials. So independent trials are identical experiments in a sequential experiment experiment. The probability models of all the sub experiments are identical and independent of the outcomes of previous sub experiments. Sampling with replacement is sampling with replacement is one category of experiments with independent trials. So independent trials simply means they are independent of each other. If one sub experiment, the next time we will do the sub experiment, so that will not be affecting the previous one or the coming one sub experiment. So let's look at with the simple sub experiment in which we have only two outcomes. So a success, as we have defined it with 1, occurs with probability p, and a failure 0 occurs with probability 1 minus p. So the results of all trials are mutually independent. So an outcome of the complete experiment, an outcome of complete experiment is a sequence of successes and failures. So that is denoted by obviously by 1 and 0 sequence, like 1 0 1 0 1 and so on is an alternating sequence. There could be any other sequence, but this is as an example alternating sequence of successes and failures. So if we denote this thing as E n naught n1, so which means that n naught failures and n1 successes, but remember that they must add up to the total number of successes and failures, or the total number of trials. So how we can find this probability of E n naught n1? It is very simple. So to understand, let's look at this very simple example. So this is example 2.19. It says that what is the probability P E2, 3. It means that we have 2 failures and 3 successes of 2 failures and 3 successes in 5 independent trials with the success probability P. So instead of P we could have any number. So probability, I know, as you know, that it should be between 0 and 1. So for the time being we have just denoted by this number. So how we can find out? So here we know that n is equal to n naught plus n1, so which is 2 plus 3, which is 5. So we have total number of 5 trials. So if you want to find out that how many of the successes we have out of 5 trials, so this will become simply a probability of we can write it as 2 3, as simply because this is failure, this is success, this is n naught and this is n1. So we are looking for the probability of success. So we can write it as 5 choose 3 possible combinations that would be there. And what is the probability of n naught means the failures. So this is failure and this is success. So we will write here as failure 1 minus P. So how many failures we have? 2. And how many successes we have? 3. So if you just put some number here, so we will get some value out of these examples. So obviously 5 choose 3, if we just calculate this number, we can have this number as 5 factorial by 3 factorial into 5 minus 3 factorial, which is 2 factorial. So we can write it as 5 into 4 into 3 factorial divided by 3 factorial into 2. So this will cancel out. So this is 10. So we will have the 10 trials which we in 10 possible outcomes, you can say, which will have exactly 2 zeros and 3 ones out of this 5 bit number, or 5, you can say 5 success and failure sequences if we make. So that would be our this means this will be a number 10. So that will show that we have in which we will have 2 failures and 3 successes, or 2 zeros and 3 ones. So let's make some note here out of this example. So as we have know that n is equal to n naught plus n1 independent trials So for n is equal to n naught plus n1 independent trials, we observe that each outcome with the n naught failures and n1 successes has probability one minus p n naught p n1. And the second point that we can infer from here is there are n choose n naught, which is essentially equal to n choose n1 outcomes with n naught failures and n1 successes. So therefore we can say that the probability of n1 successes in n independent trials is the sum of n choose n1 terms each with probability 1 minus p n naught p n1, which is essentially the same as writing 1 minus p n minus n1 p n1. So this is essentially the same as n naught, because n is equal to n1 plus n naught plus n1. So we can write it alternatively, so that will have no issue. So let's define a theorem to complete this definition. So it says theorem 2.8, the probability of n naught failures and n1 successes in n is equal to n naught plus n1 independent trials is probability of E n naught comma n1, which is equal to n choose n1 1 minus p n minus n1 p n1, which is equal to n choose n naught 1 minus p n naught p n minus n naught. So these are essentially the same if you look closely, because again remember that n is equal to n naught plus n1. So this just shows that how many failures we have, this shows how many successes we have, so they will define in the same manner. Okay, let's look at example. Next example. So I will paste it from the book here. It says that to communicate one bit of information reliably, cellular phones transmit the same binary symbol 5 times. So thus the information 0 is transmitted as 0 0 0 0 0 and 1 is 1 1 1 1 1. The receiver detects the correct information if there are more binary symbols are received, if 3 or more binary symbols are received correctly. So if less than 3, it will discard it. So what is the information error probability of error? We need to find if the binary symbol error probability is q is equal to 0.1. So there is this is 1 bit, second, third, fourth bit. So these all 5 bits represent 1 bit that have been transferred as 0. Similarly, this is 1 2 3 4 5 bits. So the question says that if 3 of them are same, means of 3 of them are same, so it will detect it as 1, or it will detect if there are 3 zeros or more than 3 zeros, or 3 ones or more than 3 ones, it will detect it 1 or 0. And error in each bit is given as with the probability of q is equal to 0.1. So q, which is the probability of error in one bit, which is given as 0.1. Now the question is that what is the information error probability E? So error possibilities are if we have 0 bit same, or 1 bit, or 2 bits are same. So we can say that in other words that we have 5 trials corresponding to 5 times the binary symbol is sent. Okay, so our on each trial success occurs with the binary symbol is received correctly. So the probability of success is P, probability of, we know is success is P, which is obviously 1 minus Q. So it is 1 minus 0.1 is 0.9. So probability of success of each bit is 0.9 and failure is 0.1. So therefore the error event E occurs when the number of successes is strictly less than 3. So if error will occur if these 3 symbols, just like I have told you in the question, that if we have when the number of success is strictly less than 3, then we will have the error, and we will find the probability of error will be probability like this: E 05 plus probability of E 15 4, because 1 is received, and probability in error 2 3. So obviously there should be the sum should be 5, sum should be 5, and sum should be 5. So that you must be careful about it. So how we can write it as 5, choose 0 with the probability that Q is 5 and P is obviously P is 0, plus 5 choose 1. In this way that will be Q 4 P power 1, and then plus 5 choose 2 with the error probability of 3, and success is 2. Now putting P is equal to 0.9 and Q is equal to 0.1, so I will just write the final answer, that would be 0.00856. Now here we can see that the probability of error in this scenario is reduced, because the error in one bit is 0.1, which is approximately or 10% chances, but now here the chance is 0.8%. So that has been reduced tremendously, and that reduction is because we have introduced redundancy. So sometimes we have to increase the redundancy so that we can have more reliability in the system. Now the same can be extended to the multinomial coefficients. For that we look at this theorem 2.9. So it says that a sub experiment has sample space S, which is equal to S naught, same that we have defined, m minus 1 previously for the multinomial coefficients. So with probability of each Si is Pi. So for n is equal to n naught plus n m minus 1 independent trials, the probability of Ni occurrences of Si with I is equal to 0, 1 up to m minus 1 is probability of E n naught. S1 occurs n naught times, so S1 occurs n1 times, S2 occurs S2 times, so on, m minus 1. So this is equal to the same way we have written the multinomial coefficient with the product of their in each probabilities with corresponding number of times P m minus 1 power m minus 1. So to understand this, let's see a very quick example. So I will paste it from the book here. So it says that it's been obviously solved here. So a packet processed by an internet router carries either audio information with probability 7 by 10, video with probability 2 by 10, or text with probability 1 by 10. Let event EAVT denote the event that the router possesses A audio packets, V audio packets, and T text packets in a sequence of 100 packets. So in a sequence of 100 packets, in this case probability of EAT is 100. Choose A audio packets, these are audio packets, video packets, and text packets. With each probability of audio packets is 7 by 10 raised power number of events, number of packets of audio, probability of 2 by 10, which is the probability of video packets with the number of video packets, and 1 by 10. So with the important thing, because these numbers are not given to us A, V, T, so we can choose any numbers to find out any of these value, but remember that this A plus V plus T should be sum up to 100. If it is not summing up to hundreds, so we cannot calculate any number out of it. So that may not be a correct, maybe we can find mathematically some number, but that would not be a correct number. So let's look at another example. So I will paste it from the book. So this is quiz 2.3. Data packets containing 100 bits are transmitted over a communication link. A transmitted bit is received in error. Either a 0 cent is mistaken for a 1, or a 1 cent is mistaken for a 0. With probability, so probability of error is given as E is epsilon 0.01, independent of the correctness of any other bit. The packet has been coded in such a way that if 3 or fewer bits are received in error, then those bits can be corrected. If more than 3 bits are received in error, then the packet is decoded with errors. So it says that let this event ek comma 100 minus k denote the event that a received packet has k bits in error and 100 minus k bits correctly decoded bits. What is probability of this for k is equal to 0, 1, 2, 3? So let's solve this problem. So here we can see that we have the k bits which shows in error or the k failures. So k bits received in error, with the in 100 trials or 100 bits, just like same as the k failures in 100 trials. So the probability of epsilon, not this, epsilon is 1 minus p, which is actually given as 0.01, and the success probability is 1 minus epsilon, which is p. So so that's the probability. So we can write it as here e sub k comma 100 minus k is which is equal to 100 choose k, and epsilon k 1 minus epsilon is 100 minus k. So for k is equal to, means no error, 1 bit error, 2 bit error, and we have to go up till 3 bits error. So we need to find the probability of these one. So that will be probability of e 0 comma 100 minus 0 is 100, which is equal to 100 choose 0, and it will be epsilon power 0 and 1 minus epsilon power 100. So if we calculate it, it will be 0.3660. Similarly, probability of 1 bit error is probability of e1 comma 99, which will be 100 choose 1 into 0.01 power 1, and 0.99 power 99. So if you calculate it, it will be 0.3700. Similarly, we can do it for e2. I will suggest do these calculations properly so that you can have some good hands-on experience. So 100 choose 2, so it will be 0.01 power 2, 0.99 power 98. So that will be, so that would be 0.1849, and similarly for 3 comma 97 is 0.01 power 3 and 0.99 power 97, and that number is 0.0610. So now look at the part B. So part B says that let C denote the event that a packet is decoded correctly. What is probability of C? So if what's given in the question, we have to look there. So here it says that if more than 3 bits are received in error, then the packet is decoded with errors. So it means that less than 3, here the packet has been coded in such a way that if 3 or fewer bits are received in error, then those bits can be corrected. So we need to find the probability that the packet is decoded correctly. So it is probability of C simply is then the sum of the probabilities that we have calculated above, means because it's given in the question that if there is no error it could be corrected, and even if there is one error it can be corrected, and even if there is 2 errors it can be corrected, and even if these are 3 errors it can be corrected. So if there are more errors then we cannot decode it properly. So we have calculated these numbers, so we'll just sum up. So 0.9819, so there is 98% chance that we can decode correctly. So I will stop here, and we will start the next topic in next lecture. So stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuh.